Expand the logs. So on this slide here, you can see that there are two logs, this one here and this one here. And our goal is to rewrite this one log as many logs. And how we're going to do that is by identifying each base in the argument. So there's a base of 25, there's a base of x, there's a base of w, and there's a base of z. So I've identified 4 different bases, 1, 2, 3, 4. What that means is that when you expand this log, you will write 4 different logs. And they all have to have the same base as the original log. So log base 5, each log will be base 5. From here, each base of the argument that you identified, 25x, w, and z, will become the argument of an individual log. So 25 here, x here, w here, and z in the last one. And that's great. We've taken care of all the bases. Each base in the argument gets its own log. But these bases, some of these bases have exponents. What are you supposed to do with these exponents? Well, you just push them to the front of a log. So this 4 here on the x would go in front of the log containing x. So 4 would be here. And the same thing with this 5 exponent on the w. This 5 would just get pushed in front of the log containing 5. And lastly, a 3 in front of this z right here. Because the exponent is 3, the power rule for logs tells us we can move it to the front. Next, I just have a bunch of logs written here. I can't just have logs. I need to assign them to be either a positive log or a negative log. So if bases in the original argument are in the top, they will have a positive log. And in the original argument up here, if bases are in the bottom, they will have a negative log. So this will turn into log base 5 of 25. It's already positive here. Plus 4 log base 5 of x minus 5 log base 5 of w minus 3 log base 5 of z. And so now this log has been almost completely expanded. You just need to double check that you can't simplify a log after that. And if you look here at this particular log, it has an argument of 25, which is just a number. And you can generally simplify logs if the argument is just a number. So this log base 5 of 25 is asking you what power of 5 gives me 25. So this here can simplify to 2. And here is the rest of the answer all written out. With parentheses and everything. So here is the final answer for this particular expansion. For this next example, on the right side of your screen, you can see that the log being used is a natural log, and that there are 2 bases in here, x and y plus 5. Oh, but wait, we have this extra thing here. So this 3, this exponent 3, is affecting x and this base y plus 5. So what was happening over here in this other example, 4 was only affecting x. So we had to put 4 in front of x, right here. This exponent 5 is only affecting w, so I move that 5 to the front of the log only containing w. Well, this 3 affects both the x and the y plus 5. So I'm going to move it to the front immediately. So this is 3 natural log x times the 4th root of y plus 5. So this 3 affects both the x and the y plus 5. And this radical is going to be really bothersome, so let's change that. This will be natural log of x times y plus 5 to the 1/4 power. The exponent on the inside of this base, on the inside of this radical rather, is 1. The root number is 4. The exponent becomes exponent over root. And that 3 is still in front. We can't get rid of that. So I'm going to forget about it for a moment, and I just want to concentrate on expanding what's on the inside here. So we have this base x and this base y plus 5. So that means I can expand this natural log out into 2 different logs. Each base gets its own log, so x gets its own natural log, y plus 5 gets its own natural log, and this 1/4 comes out to the front. Right? We moved all these exponents over here out to the front, so I'm going to move this exponent out to the front. So 1/4 natural log of y plus 5. Now, way back at the beginning, I said this 3 exponent here affects the x and the y plus 5. And it's still like that. When you expand a log, that 3 will get distributed to each log. So what happens is you will multiply the numbers in front of the log by 3. So the final answer here will be 3 natural log of x plus 3 times 1/4 is 3/4 natural log of y plus 5. With this slide, we will be condensing 2 different logs. And so we're just going to go in reverse of the thought process used to expand logs in the previous slide. So I'm actually going to start with this with this right example first. Whenever you condense logs, you will condense into 1 log. So I'm just writing 1 natural log. It looks like I have 4 natural logs here. I will be turning all these 4 natural logs into 1. And so just like when you're expanding, if something is in the top of the log, it'll get a positive in front of it. So something like this here, this positive log and this positive log. And if it's in the bottom, it'll get a negative log, like this log here and this log here. But the only thing that we're really going to be moving are the arguments. So you can see this argument x minus 3 has a positive in front of it, so I will be writing x minus 3 in the numerator. And over here, I see another positive log, and I have a base or an argument of x, so I will be writing x. And I'm not adding or subtracting or doing any crazy operation here. I'm just going to write them next to each other. So x minus 3 and x. And in the bottom, I'm going to write x plus 2. And I have another negative log over here, and the argument is y. And again, I'm just going to write those next to each other. So when you're condensing into 1 log, the sign tells you where the argument goes, either the positive log tells you it goes in the top, or the negative log tells you the argument goes in the bottom. The only other thing we have to take care of here are these numbers that were happening in front of the natural logs. Well, those become exponents. So the 2 would become an exponent on x minus 3. So I'm just going to write a 2 here on that x minus 3. And the x here would get the exponent 4. So I'm just going to write the exponent 4 here. And lastly, there's only one more number in front of a log, and that's this 1/2. But that x plus 2 would get the 1/2 exponent. You can see over here this natural log y has no number in front of it, so I don't need to give an exponent to that y. And so here is my final answer on the condensed log. Now the example on the left side of your screen, I see 1/2 times this set of logs. Well, you can either distribute that 1/2, or you could just combine these logs first. Either way, you'll end up with the same answer, and both ways are good ways to do it. How my mind works, I see that I want to combine these logs first. These are both positive logs, so when I condense them, x and y will both be in the top of a fraction. But if there's nothing going in the bottom, we don't really need to write a fraction. We can just write them next to each other like this. So we've condensed that, but this 1/2 is still here. What happens to this 1/2? Well, just like the 2 became an exponent on x minus 3, and the 1/2 became an exponent on x plus 2, and the 4 became an exponent on x, the 1/2 will become an exponent for this whole thing. So we can just move it up. This is log xy to the 1/2 power. And that's it. There's your answer. On this slide, I will briefly talk about the change of base formula and how to use it to approximate different logs. So here, to use the change of base formula, you will simply calculate the log of the argument and then divide it by the log of the base of the original log. So right, log of 4,000 over log of 12. And when you do that, you just need to type this expression into any calculator that has log capabilities and get 3.33, about 3.33. And in this other example over here, we have log base 1/2 of 7. So this would translate over to log of 7 over log of 1/2. And again, you can just type this in on any calculator with a log function, and you'll get about negative 2.81. One thing that you'll want to keep in mind as you go through and estimate what these logs are equal to is just keep in mind how many decimal places you'll be asked for. I only went out to 2. You might be asked in the future to go out to 4 decimal places for whatever reason. Math really enjoys making students and professors and teachers estimate logs out to 4 decimal places. But there you go. This is how you can estimate these. Log of argument over log of base. On this slide, I will solve a couple equations here. And I want to start on the left, as this will be a lot easier. So as I read this, log base 4 of x equals 3. This x is inside of a log. This 4 is a part of this log. This 3 is just kind of sitting over here having nothing to do with logs. It's not a base of a log. It's not in the argument of a log. And that is going to force us to have to rewrite this log equation in exponential form. So in order to do that, writing a log in exponential form, first thing is identify the base. So the base here is 4. So the base of the exponential form will be 4. The log is always equal to the exponent. So that means 3 here will be the exponent. What gets the exponent down here in our exponential form? The base. So the base gets the exponent, and we've taken care of log base 4, we've taken care of the 3. The only thing that's left is this x here in the argument, and that's what will equal the exponential part over here. So x equals 4 to the 3rd power. Easy enough, that's just 64. There's your answer. And I circled that prematurely. What you need to do with your answers with log equations, if you have a variable inside of a log, is that you need to substitute this in here for x. Here's my original equation. If I substitute 4 in here for this x, will the argument be positive? Yes. So now I can come over here and circle this as being the correct answer. All right, this next example on the right also has an x inside the log. There it is, log of e to the x minus 3 power. Now, depending upon whether or not you see it, you can do this a couple different ways. What I think most students will end up seeing is that this is a log equation and it should be rewritten in exponential form. And that's fine, you just have to remember that natural log has a base e. So how do you write this in exponential form? Well, you take the base of the log, e. You'll remember that the log is always equal to the exponent, so e to the 5th equals the argument of the log, e to the x minus 3. Huh. Would you look at that? We have somehow turned a logarithmic equation into an exponential equation. But because this exponential equation only has one base on both sides, and they're the same base, we get to cancel these bases out and create a new equation solely based on the exponents. So 5 equals x minus 3. Well, if you solve for x here, x will be 8. Now we have to go back and check. We must go back and check to make sure that the inside of the log, the argument, will be positive if we substitute 8 in here for x. So e is a positive number. It's about 2.71. 2.71 to the 8 minus 3. 8 minus 3 is 5. A positive number to the 5th power, that'll be positive. So this is a good answer. Now, if you see a shorter way of doing this, being the natural log of e to the x minus 3 equals 5, this can be reduced right away. This expression. If you have an exponential part inside the log, right, e to the x minus 3 power, so we have an exponential piece as the argument, and the base of the log matches the base of the argument. So since they match, your answer here will just be the exponent. This is a much faster way to find that x will equal 8. On this slide, a couple more equations to solve. One thing I like to do is use parentheses. So I'm going to put parentheses around this 5x and this 4 first. That way you know everything is inside a log. So here I have natural log of 5x minus natural log of 2x minus 1 equals natural log of 4. Well, this 5x is inside of a log, this 2x minus 1 is the argument, this 4 is in the argument. All of the bases are e because they're all natural logs. Okay, well, I mean, let's see what happens. I mean, I just got done learning here that I can combine these natural logs into one. So natural log 5x has a positive log, so I'm going to put that in the top. 2x minus 1 has a negative log, so I'm going to put that in the bottom. And this equals a log of 4, the natural log of 4. All right, well, I have one log on the left, I have one log on the right. Everything is inside a log, this 4 and this 5x over 2x minus 1. It's all inside of a log. And since they are the exact same log with the same base, base e, I can reduce the logs away from both sides, leaving me just with this new equation, 5x over 2x minus 1 equaling 4. So what's going on here? Well, I can solve for x. I have not liked fractions the entire time I've been studying math, so I want to get rid of this fraction. I'm going to do that by multiplying by 2x minus 1 to every single term. So that gets rid of the fraction there, and I'm going to distribute this here right away. So this is 5x equals 8x minus 4. So I can go ahead and finish solving this log equation by subtracting 8x and then getting what? Negative 3x equals negative 4, and then dividing both sides by negative 3 to get x equals 4/3. Now I want to believe that this is going to be a good answer. I have to check. So if I put 4/3 in here for this x, 5 times 4/3 is 20/3. That's a positive number. So it works in this log. I also have to check this one. Well, 2 times 4/3 here is 8/3. 8/3 minus 1 is 5/3. Again, it works out just fine. This x results in a positive argument for this other log here. So this is a good answer. Over here on the right side, I have this exponential equation. And I know it's an exponential equation because I have x in an exponent. No logs. So this is definitely an exponential equation. And normally what you try to do with an exponential equation is make similar bases. So you're trying to make 4 base e. The other way of saying that is, what power of e gives 4? What power of e gives you 4? I have no idea. And if you are having trouble trying to figure out what power of e gives you 4, you're probably going to have to rewrite this equation in log form. So I see here my base is e, so that's going to lead me to write a natural log. And I know the log will always equal the exponent, and the exponent here is x minus 1, and that this 4 will go into the argument. So from here, I'm almost done. I have to isolate this x. So that just means I'm going to be adding 1 to both sides and get natural log of 4 plus 1 equals x. Now, since I started out with an exponential equation, I don't need to check this answer. All the work is right. This is my answer. Everything is awesome. But what I do need to do is sort of make sense of what this is. Natural log of 4 plus 1, that doesn't make any sense in the real world. If you walk up to a regular person in America, you say, hey, I just found natural log 4 plus $1 laying on the ground. Nobody's going to understand what you're talking about. So what you need to do is type this into a calculator and get either x equals 2.38 or 2.39 if people teaching you this are sticklers for rounding. But to go back to my example, my money example, nobody's going to understand when you say I found natural log of 4 plus $1 on the ground over there. But if you walk up to somebody and say, hey, I found $2.38 or $2.39 on the ground over there, people will know, people understand what these values mean, not so much these values. So the difference between these is that this is an exact answer, and you can tell it's exact because it has a log. That's what makes it exact. A natural log of 4. That's a very precise number. These are just approximations. And they are approximations because there are some decimals there. So these two answers are approximations. And that's how you can tell the difference between exact answers and approximate answers. And one way to get approximate answers after you do a bunch of solving like this is to use the change of base formula. That's why we mentioned it a few slides ago there. And just to make sure you understand what's going on with that change of base formula, I'm only going to do this one here. I'm going to set this one up for you guys to try over there out in YouTube land. So here again, with this particular question, I'm pretty sure I want to get a base of 5 on both sides if I can. But I don't know how to turn 210 into a base 5, because this question, what power of 5 equals 210, I don't know. I know 5 to the first power is 5, that's not 210. 5 to the second power is 25, still not 210. 5 to the third power is 125, still not 210. 5 to the fourth power is 625. That's way too big to be 210. So it's not going to be a whole number, so math. So what do? You rewrite it as a log with a base. The base of the log is the same as the base of the exponential piece. So the log, base 5, will equal the exponent, x plus 3, and the 210 will go inside the log. So again, almost done, almost done. We need to isolate this x. So again, it's pretty simple. You just have to subtract 3 from both sides. So this will be log base 5 of 210 minus 3 equals x. Now in the last example on the last slide, we could just type in natural log because natural log is a button on a calculator. But this we can't do on a calculator. This requires the change of base formula in order to solve it, to approximate it. So log of the argument over log of the base minus 3 equals x. Now, if you're doing this at home, I would recommend figuring this out first and then just coming along and subtracting 3 from that. And if you do that, you'll get that this fraction is 3.32. I'll go out one more decimal place, 3.322. And then you'll take away 3, and that will be x. And then this will be 0.322 equals x. So here's your approximate answer here. Whereas this one up here, before you start using change of base, would be your exact answer. Now, what does this mean? You could substitute this 0.322 in here for x and get 5 to the 0.322 power plus 3, and that should be close to 210. It's not going to be exactly equal to 210 because we rounded. I only rounded to 3 decimal places. So I'm going to do that off video and come back with a result. And it is 209.88. So if I take this answer and I'm feeling like, man, I really want to check this, I can substitute it back up in here for x. And when I did that, I got 209.88, which is really close to 210. Again, since we rounded this number to 3.322, this is not going to be exactly, it is approximately 210, just like the answer is approximately 0.322. So very quickly then on this other problem over here on the left, you can see that this 4 is the base of a log, this x is in the argument of a log, this 4 is the base of this log, this x minus 6 is the argument of this log, and this 2 doesn't belong to any log. Again, when you have a number just sort of floating around, not belonging to any log in a log equation, this is your clue that you will rewrite in exponential form. But the problem is you can only rewrite when there is one log. And right now we have 2. So you have to combine those two things, 2 logs together. So you'll have a log base 4 of x times x minus 6 equals 2. Now that there is one log on the left side, this can be rewritten as an exponential equation. So 4 is the base, the log equals the exponent 2 equals x times x plus, minus 6. There we go. So you could go through and solve this whole equation here, and I think you would get 2 answers. X equaling -2 or 8. So then you have to check, does -2 work as an answer? Well, -2 would not work as an answer, because if you put that answer in here for x, the argument becomes negative, and it's even worse over here. -2 minus 6 is -8. That's definitely a negative number, so this answer does not work. However, if you consider x to equal 8, if you put 8 inside this argument, the argument is 8. That's a positive number. Check. It works here. If you put 8 into this argument, 8 minus 6 is 2, also positive. So this answer is a good one.